Hello and welcome back. So now we move from geometry preprocessing to the meshing and simulation stage. So you should have this folder in 3 mixing elbow, and here you have these 3 cases. We focus in V3. This is the one that, let's say, most standard one with the options to work and everything. In each case, there are differences, mainly related to geometry. This is the one, let's say, final geometry. So here you go, you open your files. We're going to focus now into the meshing files. So if we go into blockMesh, we have these domain dimensions. Okay, so this is my external mesh. And look at that, the delta X is 0.2. So basically it will be the outer box. So that will be, this is external, internal aerodynamics, no? So pretty much it will be up to you. How do you want to define that? Okay, so in this case, a box can be very large or small. As I say, a good practice is to make the faces matching to the boundaries, but make it a little bit larger because if you put it there and for some precision, it can cut your surface. So it's not anymore the geometry, but it's up to you. My practice is I make it a little bit bigger. This case is it's too much, but it will be up to you. So here we have this box, okay, and let's see how it looks like that box. So remember blockMesh, and then I go, okay, let me go because I think I have already a solution. And started, so let me do blockMesh and let's see how it looks like. Okay, so I'm taking here, now this is my blockMesh. Let's go to snappyHexMesh, and here I'm reading this geometry. Okay, so this is a geometry where I already have all my regions inside. So it's the OBJ normals are oriented in the right way, so there is no problem when it comes to normals or if the surface is open or so on. So there we go, build in, apply, then this, and then let me go constant geometry, and this is my geometry. Okay, so basically this is what we have. So see that in this case, make it a little bit about one cell here, here, and here, and here. So that is my standard practice. But look at that later. We're going to talk about some small problems. So this might become a problem. It's not like okay, you need to have it perfectly matching, but you will see later that it can give you some problems or more iterations because it needs to do more corrections when it comes to the snapping and so on. But it's not a big deal. But if you can have everything matching, no, the cell size will be perfect. So here is perfect, perfect. Here you might have some issues. So at this point, if we go here, let's read it. So we're doing all the 3 steps. Remember, this is ready to go. We have the OBJ. These are the surfaces. And recall that this is the surface I prepare. And I have that patch there. So let me reopen that. So everything already have the naming convention and so on. Open here. And if I go here, regions, see that you can access that patch. Okay, you have everything defined there. I will leave it open. Then I go here. I access the patches. I know my names, standard options, nothing to change. Now here features, okay, the edges. So see that I have mixing elbow image. So it's the whole geometry. Okay, and just to show you something here, so that will be surface features, my whole geometry. Okay, we already saw that. But then I apply these levels, and this is how I recommend you to apply. Later, we're going to see that this might work, might not work. So this is the best way. So always use levels. So remember, first one is the distance, normal from the edge, and this is a refinement level. So as you put 0 is here is going to enforce only the snapping. Okay, then see that I have this ring. So this is the whole stuff, and this is the ring, and see that I have different refinement. So how did I create that one? We saw in the previous video, but just to show you that when you run surface features, uh, it's going to create this folder here where you have the OBJ files. Exactly like we did in the previous video, you can access those OBJ files. So just to show you, the information I extracted in that step is this one. These are all the edges that is going to be they are going to be captured. But for instance, if I want to extract another edge from this extraction I already did, or you can take your steel off to you. Remember, this step here, let me select here. There you go, select it, extract. There you go. Now convert it to filter, alphabetical, structure face, and then you can save it as OBJ file here. Let me go here, save data, and there you have the OBJ. Okay, so pretty much that is what I did. So look at that. Now I have local control. So you have all the image, or you can manipulate this one and say, okay, I just want this or this. So see that you can have a lot of control. My patch also I can access, I extract it, but I'm not putting anything there. Then surfaces. So I have this global surface that I read here with this name. So I apply global parameters, and then I can access local parameters. So I have pipe small, and recall that in my geometry, pipe small is this surface here. And I want to point out something, that many problems that you're going to see are, we have seen that that aspect ratio is very important when growing the boundary layer. And many of those issues are related to curvature. When you have a lot of curvature, you might have no cell collapsing, but basically because the aspect ratio is changing. In snappyHexMesh, you have used some other commercial software, probably you're familiar, that they recommend not to add, for instance, one cell every 18 or 15 degrees. No. So that is a good practice if you are using a full unstructured solver, but this is not fully unstructured. Here you have the transition from the small cells to the large cells 2 to 1, okay? So that can give you a lot of problems. So my standard practice, when I have a lot of curvature, I like to have one cell every 10 degrees. So basically from your geometry, now you start to see how important is knowing your geometry. You can get an idea about that. So let me go here in this sketch. Okay, and let me go here, put a line from here, and a line here, and a line here. So let's say that in my case, if I am aiming, so let me select this too, for 10 degrees, this distance, oops, here, in average should be 0.05, let's say, and that should be okay. If you go for 20 degrees, this is what happened. But look at that, and what I was telling you, that you have this tree data structure that is 2 to 1. So if you go from refinement level, let's call this refinement level 1, and then you go to refinement level 1 level below 0, it will become 40. And look at that, it's a huge jump. And it's the same that happens here. 20, and probably you're going to have 10. So you might be aiming to this, but for whatever reason, there will be some jump and will jump to 20. And this is where you're going to have problems and that collapsing that you very often see. And later we're going to see that one. So you can get an estimate, what will be your edge size, my standard practice in snappyHexMesh, and I aim for 10 degrees. Add an element every 10 degrees. So the logic here it was, in the large pipe, I don't need it because it's already okay. But the small pipe, okay, I need to put 3 to get that. And just to show you, remember we have this Excel worksheet here. So my background mesh is 0.2. If I put 2 here, I have 0.05. We have seen that that is okay. So for the large pi, it's okay, but 0.05 might be a little bit on the limit, okay? Because I will have some transition. So there I am aiming for 0.025, which is even better, okay? So that was my logic there. I already know well how these things work. So let me close here, and we keep reading. Okay, so hope you have a good idea what is happening. You access the region, then refinement region. So here, I'm not putting anything, but if you want, you can read your whole mix enable or geometry and say that inside my body, I want everything 3. I'm not going to put it later. We're going to see what it changed. Let's say this is the minimal case. Then also remember, if you want to put a surface on top of a surface, 2 different STLs, do not do it here. Okay, here you can do it because I am accessing the regions. But if you read another STL pipe small, it's going to give you some issues. So it's better to do it here. So in this case, look at that. You have my patch. You can read it outside and then use distant refinement. Okay, this is the way to do it to have better control. This point now also, it is inside the geometry. Okay, so I put it somewhere inside the geometry. If you put it outside, it will do the external mesh. If you put it inside, it will be the internal mesh. Okay, very important. Find that point. And whoops, these are standard options. This we have seen how it works. And look at that, these are local parameters 1.2, 1.9, 1.1, and they can have different values. It's clear different values is not the way to work because you can have problems, but you can have local control. So as you can see, there is a lot of control that we have in snappyHexMesh. What we have missing is a nice GUI that later will be another tool that I use, a very nice cloud-based GUI. And then also I have to criticize a lot the transition 2 to 1 is extremely problematic. And then the enforcing of the aspect ratio is another issue. But if you understand well, as we have seen how things work, I think you can get good meshes. Standard for me, standard for me. Okay, so nothing to do. Let's do the mesh. Then you have here the scripts. So you have run mesh parallel and run solver. So we do the mesh and then we run the solution. So here are your steps. So let's run the steps for the mesh and then we do the simulation. So this is a fast mesh. Okay, by the way, it's running in parallel. And there you go. So I always recommend to save log files. You have a lot of information, and now you're getting the idea how this aspect ratio, this refinements works. If you read the log file, you can identify where do you have the errors and so on, and you can modify, your parameters or adjust your geometry accordingly. So look at that. My boundary layer mesh is pretty much very good. It's almost perfect. So small issues. Remember that not always this is 100% telling you the truth, but always visually check. And that's it. So you have here your distances and so on, but later you can control that with your Excel worksheet. And using all relative sizes and so on, you can control everything. So for all matters, this is perfect mesh. And let's visualize what we have. Parafoam built-in. Then I go here and low state. I have a state here. Mesh. Okay. And there you go. This is what we have. So as usual, well, let's look at here. First, nice boundary layer here. The surface, you see your refinement level. You see that like your boundary layer, your inflation layer. It was generated. No problems here. Look at that. As I didn't put this inside here that I mentioned, I'm getting that transition. But as you put this way, it will be all uniform inside. And this is what I recommend you, and that is a standard practice. Do it like that. Don't have this, especially in internal flows. And external flows, probably you can digest this better. But look at what is happening here and what I mentioned, the transition 2 to 1. Look at that. You go from this cell to something large very fast. So you're doing the scale resolving simulation, less stuff like that. This will completely destroy your solution. Not completely destroy, but it will add a lot of transition. And these are issues, numerical diffusion. You are transitioning too fast. So what happens, Snappy will try to add some polyhedron, can be any shape, to try to control that, but it's not done like in full unstructured solvers, meshing tools, that controls that, and you have a nice growth rate of 1.1, 1.2, or whatever. Here is brutal. It's 2 to 1. And that is an issue. Okay, that is a problem. And this, you're going to have it all around. So I think here you get a better idea. Same stuff here. So see that you go from a small to large very fast, 2 to 1. There is no transition. Okay, a small transition going from 0.1, 0.11, 0.12. No, here you go 0.1, 0.2 fast. And then some small issues here that you will have in your boundary layer growing, but as you see, this is almost perfect. Okay, besides this one, as I mentioned, that look at also here that I grew here in that specific edge. This is why I added there, because I know that there usually I may have some problems with boundary layer, but also how is everything is resolved. I added this one, no image, and then I say a distance 0.1 from that feature, put a refinement level of 4, and then a distance 0.2, put a refinement level of 3. Okay, so here you increase the distance and you reduce the refinement, and you see it clear, 0.4, 0.2 there. Okay, to have a nice transition, but it's always 2 to 1. Okay, so kind of there I was trying to control that transition, now the growth rate, but it's 2 to 1, it's brutal. So here you have the collapsing, and let me show you what is happening here, because if you look here, you start to look at the surface, you already see the issues there. So let me go here, let me put this. Look at what is happening here, that even so that we want to force the solution of the mesh to be uniform. Look at that, you have large cells and small cells. And usually this collapsing, when you look at here, you will see that the collapsing, you have it in that transition. Recall aspect ratios are very important. So you have this one, that it will have a large X size, a small X size. So these are two different aspect ratio. And then when Snappy start to control the quality metrics, it's going to give you problems. So remember, this aspect ratio will be measured the largest edge, or probably you can take your diagonal of the element, and then is the ratio between the largest and the distant normal to the wall. So this one will be aspect ratio will be largest in this case. In this one, it will be smaller and so on. So look at that, what is failing here. Large to small, and you have that collapsing. So this is the stuff that are difficult to control, and that's why this transition 2 to 1 is problematic. It's not an issue. Okay, you have small cells that are collapsing, so I don't worry about that. I will worry if I have the whole region large. Okay, that is a problem. I need to modify that. So here you can see that you have a lot of information, and the missing one, it was curvature now. So let me go in the meshing one step back. Okay, so here I don't have the boundary layer. So what is happening is adding that inflation layer, okay, controlling those quality metrics. But see here that you have those different transitions. But what is interesting, let me go back to the Cartesian mesh. So in the Cartesian mesh, you see that everything here is perfectly uniform, okay? The problem now is the snapping, and you can identify now, oh, okay, instead of going and doing all the 3 steps at the same time, I can stop in the snapping, and probably you can change one of the quality metrics or parameters, keywords that control the snapping phase to get a better snapping, because clearly here you start to see that the problem is the snapping, okay? And if I put there, let me also load my geometry. It's this one. Let me add some transparency. We have there the geometry in top, and to show you here what happens in the snapping. And when I was saying that, try to make it also the mesh body fitted to the body. So see what happens here, that the mesh is a slightly bigger now when it does the snapping than your STL. It's not a problem, but then you will see that the solver, the mesher needs to iterate more to get that perfect fitting. So if you go to the next step, see that it's perfectly matching, but it's doing more iterations. So it's a good practice if you can control that and get that matching is better. And here you see that there's these issues. Look at what is conserved there. So all these issues that you have in curvature are related at this point to the snapping phase. I have to be honest, it's difficult to control that snap and see that very different. You know, you go from large to small. Small, usually the smallest one would be this distance. Then the largest. There is one correct, by the way, in this Excel, this correction that you see here, it should be curvature correction that I was getting that, but it's very difficult to get that curvature correction, so you can add your own factor. So this is what is happening. And when you have that collapsing, usually is related to the aspect ratio here in those transitions. But I think pretty much is a very, very nice mesh. Okay. It's not the perfect, it's not what I will use. Okay. Later in the next video, we are going to go and push, use the better mesh and so on. But this is a fully working case. So at this point, we're done. I think I don't need to discuss everything. We have discussed all parameters, the curvature you have seen here. I hope you have a good idea, a better idea. The only thing that I think we're missing here is this. This one, and I'm going to touch this one, and there is another also refinement span, a new option in more advanced videos. But for the moment, we don't need that. Okay, and basically this, what it's going to do is add more refinement where you have very close surfaces. So basically, if I enable that, it will add more refinement here because it is the spacing, it's a small, but we need to dedicate a specific video to that feature to better understand. So at this point, let me close here, perfect mesh, everything, and let's run the simulation, okay? So we're ready to go. We have this script here, okay? So it's this one, you will see the steps. So look at that, what I'm doing is moving the file from one place to the other, renaming, and then running parallel. I already created the boundary file, my boundary conditions. So if I open this file, see that the patches, all the patches that exist in my mesh, I have it there. So I know that I have this region. So inlet 1, inlet 2, outlet. So I created, so I don't need to say anything about this. And that's all. Okay, so this is a template. Get your files, put there, and just put the right names. Okay. Then also let me run the case because I need to sh run solver. Then it's doing some reconstruction, so on. And from here, I would like to, it's already running. Okay, so I would like to access also the boundary file, polyMesh boundary. So see that here I'm running. Okay, I have a turbulence model. Look at my y plus. So probably it's very low. So I know I can make a quasar inflation layer now. So if you make it a quasar, you are going to avoid all those problems that you saw. They're going to disappear. Mass flow, what is going in is going out. So this is pretty much for me, it's a standard case setup now when it comes to function objects and so on. So you have everything there running perfect, no issues. What I want to talk about is the boundary file. So in this boundary file that is created at meshing time by Snappy and blockMesh, okay, you have all this information. So see that all the patches that you need to put in boundary conditions, you have it there. You have it named in there. So you have 6 patches, inlet 1, pipe large, outlet, pipe small, inlet 2, my patch, okay? You have it there. So you need to use all those names here. But it's also important that you have here this keyword. This keyword also you can change it. So if you know that you are going to use a Dirichlet or Neumann boundary condition, call it a patch. So on the inlet, it's a patch because I'm going to impose a numerical value. But then you have pipe large, pipe small, and my patch. Those are walls. Okay, so walls is a constraint type. I call it wall here. And then that wall type will let me use specific models, like in this case, it's the turbulence modeling. And that's all. Then you can have also symmetry that we saw in the previous cases and so on. So this is how you set up your case. So you have to be very careful of modifying the file. This you need to do it manually, and you do it manually because it is you, the one that is thinking about what are my boundary conditions. Okay, so I think that requires a specific video boundary condition because it's the most confusing part, honestly, in OpenFOAM. But any case, remember Dirichlet or Neumann, put a patch. So you have a physical wall, call it wall, and if you want to use symmetry or you're working 2D, it is empty. So empty and symmetry will be the same across all these files. Instead, wall also will be the same. Well, it's not the same. You have a specific entries to enable those specific models, and then patch, you have a gazillion types of boundary conditions. So you need to look for, in this case, fixed values. A num is a Dirichlet, and this is a Neumann. So these are the most basic one, but then you have many types. So that's all. We have a solution, okay? And let's do the post-processing. Built-in here. Load state, part of view. Here I have this one to post-process the solution. Remember, check here that you're pointing to your file in your directory. So it should be pointing by default, but you never know. And this is it. everything makes sense. So let me go to the first step, and then you see the solution. So by the way, this is a steady solution now. So I'm not resolving in time and looking for the steady solution, and kind of this is what we have. Everything makes physical sense. So recall that here you will have a problem with the boundary layer, but see that in the solution, it's not going to affect your solution. Okay, it's not a big issue. Okay, so don't worry about that unless it is something really big. Shouldn't be too worried about that. Then what I was mentioned, let me go here. If I put here, let me put crinkle slice, this one, crinkle slice, let me add here, and let me add this one. And this is an issue, this transition also. I want in the this transition from a small to large, okay? That is going to add diffusion. And you can look at here, when you're passing from something small to large, you will see a large numerical diffusion, okay? So again, it's not a big issue if you're doing runs, if you're doing less, might be an issue, but also this can be reflected in the surface mesh quality. So it's better to have everything uniform. Okay, so yeah, this is all for this case. I guess at this point we cover a lot. This is the mesh now that we have running. Now we're going to revisit this one and try to solve or add different errors. What would happen if I do this or that? But you have all my standard practices at this point, and this is how you should work. So thank you very much for your attention. See you next video. Bye.